As the title of this episode suggests, I'm going to be going over U-substitution expanded. Before we learned about kind of a basic problem involving U-substitution, it was a indefinite integral. It wasn't too complicated. I'm going to go over three examples. Two of them are going to be definite integrals, and the last one is going to be an indefinite integral, so we don't have to change the bounds or anything, but we have to evaluate a pretty complex um, indefinite integral, and we're going to have to do types of two types of substitution. Okay, so this one here, we're taking the definite integral from 0 to 1 of e to the x minus e to the x dx. Okay, so the first thing we're going to do is we're going to look at what we see twice. So there's an e to the x here and an e to the x here. So typically when we see something twice and we're trying to do a u substitution, we want to set that thing equal to u. So u is going to be equal to e to the x. And du, remember the derivative of e to the x is just e to the x. So it's e to the x dx. So what we have here, when we say the integral of e to the x minus e to the x, what this is really is using our power laws is the integral from 0 to 1 of e to the x times, right, times e to the negative e to the x dx. And if we know that we set u equal to e to the x and du equal to e to the x dx, it's going to be the integral, right? We'll think about the bounds in a second, but if e to the x dx, right? If e to the x dx is du, then that's going to cover this part and this part. So we have our du. Now all that's left is this e to the negative e to the x. So if u is e to the x, this is going to be e to the negative u, right? And now if we think about our bounds, once we change this from a expression in terms of x into an expression in terms of u, we have to plug in 0 and 1 from our bounds into what u is. So our upper bound, right? Our upper bound was 1 before. That was our x variable. So if we were to plot that on a graph, 1 would be here on our x-axis and 0 would be here on our x-axis. Now if we go to like a u-plane, right, now we're in the world of u, we have to plug in 1 and 0. So e to the 1 would be e, so that would be your upper bound. E to the 0 is 1. So now we're in terms of u, we're in the u world. Okay, and on our axis, it would be e, and it would be 1. Right? So instead of 0 and 1, we have to put e and 1. So 1 is now our lower bound, and e is our upper bound. Okay, now if we want to integrate this, well, remember, e to the negative u, if we're taking the integral of that, we could call like v negative u. We could do another substitution, and we would figure out that this is the same as negative e to the negative u. Much like d by du of e to the negative u would be negative e to the negative u. It's the same thing, we're just going in the opposite direction. Okay, and remember, we're evaluating this. We're not doing a plus c because it's a definite integral from 1 to e. So this would be equivalent to e, right, to the negative e minus e to the negative 1. So e to the negative e, let me just calculate that here. So e to the power of negative e, that's 0.066 minus e to the power of negative 1. Okay, so if we do all this, I'm actually going to do it in one step. This is going to be negative 0.3019. So this would be your answer here. So that's how you do a U-substitution for a definite integral. It's the same thing as an indefinite integral, except you have to change your bounds by plugging in what your original bounds in terms of x were in for your u expression. And you actually evaluate it numerically and analytically. Okay, let's look at this one. So this is a composite function. Okay, we're taking tan x times the natural log of cosine of x dx. So typically if we see a composite function, we're going to set this whole thing equal to u. So u equals the natural log of the cosine of x. Now remember, when we're taking the natural log of something and we're trying to find the derivative of it, it's going to be 1 over that thing. So 1 over cos x times the derivative of the inside. So d by dx of cos x, remember, that's negative sine x. So this is going to be times negative sine x. And we can kind of simplify this. Instead of saying times negative sine x, and then, instead of saying 1 over cos x times negative sine x, this is just negative sine x over cos x, or negative tan x. And we can't forget our dx, of course. So negative tan x dx. Okay, and notice that we see tangent over here, and we see dx over here. Okay, so if we bring a negative out in front, that should take care of the tan x and the dx. Okay, so it'll be negative, and then the integral, and we can have our du. Okay, and then the natural log of cos x is our u. So all we have now is negative integral of u du, right? Because u was this entire natural log of cos x, so that's covered. Du was this tan x times dx, and it was negative, so we tag this negative out in front. Now the only thing we have to change is our bounds, right? So if our lower bound was 0 in our original integral, we have to plug that in. Remember, u was the natural log of cosine x, so we have to plug that in for x, so cosine of 0. The cosine of 0 is 1, and the natural log of 1 is just 0, because e to the 0 is 1. So our lower bound is still going to be 0. Remember, that's not always the case. We have to actually check. Okay, and now our upper bound is pi over 4. So u is the ln cos x, so it's going to be ln cos pi over 4. Okay, the ln of, remember, cosine of pi over 4, if we have our special triangles, let me just make it a little neater here. This is our special triangle here, and we had pi over 4. Obviously, this would be pi over 4 as well, if we had a 90-degree triangle. This would be 1, 1, and root 2. So the cosine of pi over 4 would be the adjacent side over the hypotenuse. So it's going to be 1 over root 2, which is root 2 over 2. Okay, or I'll actually write 1 over root 2. So it's the natural log of 1 over root 2. Okay, we can write this as an exponent. So 1 over root 2 is the same as 1 over 2 to the half. And this is the same as 2 to the negative a half. So this is the natural log of 2 to the negative a half. And remember, it's a natural log, so we can bring that out front. It's going to be negative ln 2 over 2. So that's our second bound. It's going to be negative ln 2 over 2. Okay. So now that we've done that, we can actually evaluate this here. So if we want to evaluate the definite integral of u du, it's going to be negative u squared over 2, right? And we're evaluating this from negative ln 2 over 2 and 0. So this is going to be equivalent to, let's see here, if we plugged in negative ln 2 over 2 for u, we get negative ln 2 over 2 squared divided by 2, and there's still this negative out front. Okay, minus, and then we have negative 0 squared over 2. So this term's going away. All we have to do is calculate negative ln 2 over 2 squared. So this squared is going to apply into both of these numbers. So once we do that, it's going to be, let's figure out what ln 2 over 2 is. So ln 2 divided by 2. Okay, we're squaring that. Okay, we're squaring that, and then we get 0.12, and we're dividing by 2. So this is almost exactly negative 0.06, and then 0.006. So this is your answer. It's always good to try and leave your upper bounds like as exact values, like negative ln 2 over 2. If you left it as a decimal, like your final answer, it wouldn't look as nice, wouldn't be as easy to compute. Okay, last one here. Definitely a challenging one, so let's just take it step by step here. So this is an indefinite integral, right? Of x over 1 minus x squared plus the square root of 1 minus x squared. So we see 1 minus x squared twice. Obviously, that's probably going to be our u. So u is 1 minus x squared. Du is negative 2x dx. Okay. Now once we do that, we know that if we want to solve for dx, to replace the dx is going to be negative 1/2 du. Right, so if we plug this into our formula here on the left, or not the formula, the expression, it's going to be negative 1/2 times the integral of 1 over, so 1 minus x squared, remember that was our u, so I'm going to write u here, plus the square root of that same quantity, so plus the square root of u, du. Okay, so now, this is not something that we can integrate right away, so we're going to have to do substitution again. So you might notice that you see u twice, like we did originally with 1 minus x squared, so we're going to set u equal to the square root of v, or sorry, we're going to set v equal to the square root of u. Because we don't want that square root there. We want to replace it with a whole value. Okay, so instead of having a square root, we're going to set that equal to some whole variable like v. Okay, and in that case, actually, instead of differentiating it right away, let's square both sides. So v squared equals u, right? Because both sides squared, we're going to get u on the right, v squared on the left. So now if we differentiate both sides, we're going to get 2v dv equals du. And we'd get the same thing if we differentiated this right away, but it's easier just to square it first. Okay. So now that we know du is 2v du, or sorry, 2v dv, a lot of variables here, 2v dv. So wherever we see du, we can just put 2v dv. So negative 1/2 times the integral, and this is going to be 2v, and we have our dv, That's replacing our du, this part right here. Now, what haven't we dealt with? Okay, we haven't dealt with this u plus root u. So if we know u is v squared, we're going to put v squared here, and we know root u was equal to v. So we're going to put plus v. Now notice we can factor out a v on the bottom, and this is going to be 2v over v times v plus 1. Okay, and we can cancel a v. This is going to be negative 1/2 times the integral of 2 over v plus 1. And I'm forgetting my dv's here. Okay, and we know that when we take a constant like 2 and divide it by a variable plus or minus a constant, that's going to be equal to, we still have this negative 1/2 here, times the natural log, right? Oh, I'm forgetting something. We can actually cancel the 1/2 and the 2. I just saw that. So see how we can also bring out this constant 2. So this is like negative 1/2 times 2 times the integral of 1 over v plus 1 dv. So these will cancel. We're just left with the negative. We're going to get negative integral 1 over v plus 1 dv, right? Remember, that's going to equal negative natural log of the absolute value of v plus 1, right, times the derivative of v with respect to v, which is just 1. So we don't need to multiply it by 1. We can just leave it, right? And now we have to start to substitute back in for v what it actually is. So remember, v was equal to the square root of u, so this is negative ln square root of u plus 1. And the square root of u, well, let's look back here. That was the last question. So u is equal to 1 minus x squared. So the square root of u is just the square root of 1 minus x squared. 1 minus x squared plus 1. Okay. And then obviously we need our plus c because it's an indefinite integral. So the first two were definite. Last one was indefinite. These are definitely more challenging problems. But I hope that they kind of made a bit more sense as we kind of dove into them. Started off in the last video with a bit of an easier one. These ones are definitely more difficult, but if we can expand kind of our problem solving skills with these types of things, it's totally going to benefit us in the future with calculus, because like I said before, I want to keep reiterating that the foundation is so important. And once we have these skills down, we're going to be able to do so much more. We can do things called like the Laplace transform and different types of series, the Taylor series, the Fourier series, all these types of super cool things that have a really neat application. But we can't do them if we don't have these basics down. So I hope that this made sense. Drop a comment if you're confused. I'm always saying these calculus videos can get pretty intense, pretty deep, pretty quickly. So let me know if you're not understanding something. I'll be sure to get back to you on that. And I'll see you soon.